Hello everyone. Today in this video we'll be seeing some basic definitions on PDE and the topic forming an PDE by eliminating arbitrary constants. So first, the definition of PDE. A partial differential equation. It is a differential equation that contains, this word is very important, two or more independent variables and the derivative must be partial derivatives. For example, let us consider this equation. Dou square u by dou x square the whole square plus dou square u by dou y square the whole cube minus x into dou u by dou y the whole square equal to x plus y. So here we can observe that the variable u has been differentiated with respect to x and y. So this u variable will be dependent and the variables x and y will be considered as independent variables. So since there are two independent variables in this equation and the derivatives are partial derivative, this equation is said to be a partial differential equation. So the next definition is order of a PDE. It is nothing but the order of highest partial derivative occurring in the equation. So note the word highest partial derivative. There may be many derivatives in a single equation. We are going to find the highest partial derivative. For example, see this equation. So here this term represents order 1 because we will be saying first order derivative of u with respect to y. So this will be of order 2. So it can be read as second order derivative of u with respect to y, and this is also of order 2. So there are three orders here, 2, 2 and 1. We will be taking the highest partial derivative as the order. So we will be taking 2 as the order of this PDE. And the next definition, degree. The degree of a PDE is nothing but the greatest exponent of highest order. So we have to note the highest order in the given equation and note the word greatest exponent also. Exponent, in other words, we can call it as power. So here, see this equation. It is of order 2, this derivative is of order 2 and the power of this order is 2 and the power of this term is 3. Greatest power represents 3 in this equation. So the degree of this equation will be 3. And next definition, coming back to the linearity of a differential equation. A PDE is said to be linear if the dependent variable and its partial derivatives. So note the word dependent variable. So dependent variable and partial derivative occurs only in first degree. So the degree of those terms should be 1 and these terms should not be multiplied together. Otherwise, the equation will be said to be a non-linear PDE. So next definition is a homogeneous or non-homogeneous PDE. If each term of a PDE contains either the dependent variable or one of its derivatives, it is said to be homogeneous. Otherwise, the equation is called as non-homogeneous PDE. So let us consider the following examples. For these examples, let us write the order, degree, linearity and homogeneity. So let me write order, degree, whether it is linear or non-linear, homogeneous or non-homogeneous. Okay. The order of first equation will be 1 because only two partial derivatives has been involved and both the partial derivatives has order 1. And the degree is also 1. Whether it is linear or non-linear, so let us go back to the definition of linearity. So see here, a PDE is said to be linear if dependent variable and its partial derivative occurs only in first degree. The degree should be 1 and also both the variables should not be multiplied together. So you can see here the degree is 1 and no two dependent variable and its derivatives are multiplied here. So this equation will be linear. And homogeneity. So homogeneity definition is every term should has either the dependent variable or one of its derivative. So if we consider that one, let us take this term xy. In this term, there is no dependent variable z and its partial derivative. So this is non-homogeneous equation. So second one, the degree will be 2, order is 1, and it is a linear equation because the degree is 1 and no two terms are multiplied together, and non-homogeneity, both the terms, it has partial derivative and there is no term without that. So it is a homogeneous equation. And coming to third one, so this is of order 2, and see here, greatest exponent, the power is 2 here, the power is 3 here, so the degree will be 3 for this equation. And linearity, this is a non-linear equation. So let us observe why it is given as non-linear equation, because the degree of the partial derivative is of not first degree, it is more than first degree. And coming to homogeneity, so this is a homogeneous equation. And here for fourth example, the order is 1, the degree is 1, and it is a linear equation and it is non-homogeneous equation, because you can see this term sin x minus 2y, there is no dependent variable and its partial derivative in this term. So this is a non-homogeneous equation. And fifth example, the order is 1, the degree is 1. So here it is a non-linear equation, because you can observe that this power is 1, this power is 1. However, the power of this term z is 2. So it will be non-linear equation, and similarly it is a non-homogeneous equation also, because take this term x, in this term x, no partial derivative dependent variable z is also not there and partial derivative is also not there. So the last one is an example for non-linear, non-homogeneous partial differential equation. So one important thing to note is that in this video, we'll be restricting our study involving one dependent variable z and two independent variables x and y. So some standard notations are there. So since we are considering z as dependent and x and y as independent variable, we are taking z as a function of x and y. That standard notation are given as follows. So there will be first derivative of z with respect to x. It will be denoted by p. First derivative of z with respect to y will be q. Second order partial derivative of z with respect to x will be r. So similarly, s is nothing but first differentiating z with respect to x and then differentiating that term with respect to y. Similarly, you can interchange that also. And dou square z by dou y square will be t. We have to note these notations throughout this video. So the first topic is formation of PDE by eliminating the arbitrary constants. So after this, I'll be taking these abbreviations: IV for independent variables and ACs for arbitrary constants. So these are some important things to note. If the number of arbitrary constant is equal to the number of independent variables in a given equation, then we'll be getting a unique first order PDE. That is, everyone will obtain the same answer. Second one, number of arbitrary constant, if it is greater than number of independent variables, then we will be obtaining a PDE of second or higher order. Third one, number of arbitrary constants less than number of independent variable means more than one PDE or of first order. So the logic is, we have to differentiate the given equation with respect to the independent variables x and y. So let us start with some problems. First one, form a PDE by eliminating the arbitrary constants a and b from the equation z equal to a square x plus b square y plus ab. So while we are starting with the solution, we have to determine the number of independent variables, which is clearly 2 here, x and y, and number of arbitrary constants are also 2. They are nothing but a and b. Okay. Since the number of independent variable is equal to the number of arbitrary constant, we'll be getting a unique first order PDE. As I have told earlier, to find the PDE, we have to differentiate the given equation with respect to x and y. So differentiating the given equation z equal to a square x plus b square y plus ab with respect to x, will be getting dou z by dou x. This is equal to a square. The second term will be 0 because there is no x here, and here only arbitrary constants are there, so this will also be 0. So this implies, based on the standard notation, this dou z by dou x term can be written as p. So p is equal to a square, or we can write a is equal to root p. That's what written here. P can be written as a square or a can be written as root p. So next one, differentiating with respect to y. So since z is dependent on x and y, you can write dou z by dou y. This will be equal to, there is no y term in this a square x. So first one will be 0. Second one will be b square, and third constant derivative will be 0. So this can be written as q is equal to b square, or we can write it as b is equal to root q. So that's what written here, q is equal to b square or b is equal to root q. Now the required PDE is nothing but we are going to substitute replacing arbitrary constants with the terms obtained in previous equations. A square can be written as p x and b square can be replaced with q y plus a is nothing but root p and b is nothing but root q. So your final PDE will be z is equal to px plus qy plus square root of p into q. Problem number 2. Form a PDE by eliminating the arbitrary constants a and b from the equation z equal to x plus a into y plus b. So in this equation, the number of independent variable is 2, which are x and y, and the number of arbitrary constants is also 2, a and b. So since both are same, we will be getting a PDE of first order. So next, we have to differentiate the given equation with respect to x. So differentiating z with respect to x, we will be getting dou z by dou x. And if you differentiate the right hand side, so you will be getting y plus b. This implies, using standard notation, we can write it as p is equal to y plus b. So p is equal to y plus b. Now differentiating with respect to y, we'll be getting dou z by dou y equal to x plus a. This implies q is equal to x plus a. Now the required PD is nothing but substituting q instead of x plus a and p instead of y plus b. So this can be written as z is equal to p into q, which is nothing but the required PD. So the next problem, form a PDE by eliminating the arbitrary constants a and b from the equation z equal to x squared plus a squared into y squared plus b squared. Number of independent variable is 2 and the number of arbitrary constant is 2. Both are equal. So you will be getting a first order PDE. So differentiating with respect to x, dou z by dou x, this can be written as, we can take u and v method. So 2x into y square plus b square. So this is what differentiating with respect to x will be getting. So this can be written as p is equal to 2x into y square plus b square, or y square plus b square can be written as p divided by 2x. We are writing y square plus b square in left hand side because that term is there in the given equation. So y square plus b square can be written as p by 2x. Similarly, differentiating with respect to y, we will be getting dou z by dou y equal to x squared plus a squared into 2y. This implies q is equal to 2y into x squared plus a squared, or we can write it as x square plus a square is equal to q divided by 2y. Okay. Now the required PDE is z is equal to, instead of x plus a square, we can replace it by q divided by 2y, and y square plus b square can be replaced by p divided by 2x. If we bring the denominator to left hand side, we will be getting 4xyz is equal to p into q. So this is the final PDE equation. Now fourth problem, form a PDE of all spheres whose radii are the same. So the equation is not explicitly given in this question. We have to first write the equation, then we have to proceed with the problem. So we all know that the general form of sphere equation is x minus a the whole squared plus y minus b the whole squared plus z minus c the whole squared equal to r square. Here the coordinates a comma b comma c represents the center of the sphere and r represents the radius. Since all the radius are same, we are going to consider this r as a constant. That means it will be a fixed value in this problem, like 1 or 2 or 3. This radius will be fixed 1 and the center can vary. So a, it will be an arbitrary constant, b will be an arbitrary constant, and c will be an arbitrary constant. So the number of independent variable in this question is 2, which are x and y. But the number of arbitrary constants in this question is 3, that are a, b and c. Note that since the number of arbitrary constants, it is greater than the number of independent variable, we will be getting a PDE of second or higher order. Particularly, we will be getting a PDE of second order because the difference between 2 and 3 is 1. So now differentiating the given equation with respect to x, we will be getting 2 into x minus a plus 0 plus 2 into z minus c into dou z by dou x. This will be equal to 0. So now we can cancel this 2 on both sides, and then this can be written as x minus a plus z minus c into p is equal to 0. So let us take this as equation number 1. So this equation is 1. So next one, differentiating with respect to y, we will be getting 0 plus twice into y minus b plus twice into z minus c into dou z by dou y will be equal to 0. We can cancel this 2. So we will be getting y minus b plus z minus c into q will be equal to 0. So since we are getting a PDE of second order, once differentiation is not enough. Again, we have to differentiate this equation with respect to either x or y. So let us differentiate this equation 1 with respect to x. So now differentiating equation 1 with respect to x. So the first equation is nothing but x minus a plus p into z minus c is equal to 0. Differentiating this equation with respect to x, will be getting 1 plus, note that in the second term, p is also dependent variable and z is also dependent variable. So we have to differentiate the second term in UV format, product rule. So first I am going to differentiate p. I'll be getting dou square z divided by dou x squared into z minus c, and then keeping p as it is, differentiating z, I'll be getting dou z by dou x, which is nothing but 0. So 1 plus, this can be written as r into z minus c plus p into p is equal to 0. So 1 plus p squared plus r into z minus c, it is nothing but 0. So z minus c can be written as minus p squared plus 1 divided by r. So this is what given here, z minus c is equal to minus p squared plus 1 divided by r. So next one, differentiating equation 2 with respect to y. Equation 2 is y minus b plus q into z minus c is equal to 0. So differentiating this with respect to y, will be getting 1 plus, similar to previous differentiation, we are going to use product rule. So you'll be getting dou square z divided by dou y square into z minus c plus q into dou z by dou y is equal to 0. So it is 1 plus t into z minus c plus q into q will be equal to 0. So 1 plus q squared plus t into z minus c, this is equal to 0. So z minus c can be written as minus q squared plus 1 divided by t. So to find the required PDE, we are doing equating these two equations. Since the left hand side of the above two equations are same, we are going to equate the right hand side. Minus p squared plus 1 divided by r, this is equal to minus q squared plus 1 divided by t. So minus and minus will get cancelled. You can write it as t into p squared plus 1. This is equal to r into q square plus 1. So this is a PDE of second order, because you can observe that this t and r is of second order. So next problem, form a PDE by eliminating the arbitrary constants from the equation x squared by a square plus y squared by b square plus z squared by c square is equal to 1. So the number of independent variable in this equation is 2 and the number of arbitrary constant is 3. Since the number of arbitrary constants is greater than number of independent variable, we will be getting a PDE of second order. So differentiating the given equation 1 with respect to x. So first one will be getting 2x divided by a squared plus in second term there is no involvement of x, so it is 0 plus, so first we have to differentiate this z. So 2z divided by c squared, and then differentiating z with respect to x, will be getting 1. So this can be written as, first we can cancel this 2 and then x by a square plus z p divided by c square, this is equal to, differentiating 1 will be getting 0 here, so this is 0. So x by a square, it can be written as minus zp by c square, or 1 by a square can be written as minus zp divided by x into c square. So we will be getting x by a square plus zp by c square equal to 0. Similarly, differentiating with respect to y, first term is 0, second term will get 2y divided by b squared, and third term is 2z divided by c squared into dou z divided by dou y. This is equal to 0. So cancelling this 2, we'll be getting y by b square plus zq divided by c square. This is equal to 0. So next we have to differentiate equation 1 with respect to x. Equation 1 is nothing but x by a square plus zp divided by c square is equal to 0. Now we are differentiating this one with respect to x. So we will be getting 1 by a square plus, let us keep the constant 1 by c square outside. Z is also dependent on x and p is also dependent on x. So we will be getting dou z by dou x into p plus z into dou square z by dou x square. This is equal to 0 using product rule. So 1 by a squared plus 1 by c squared into, this can be written as p into p plus zr. This will be equal to 0. So 1 by a square plus 1 by c square into p square plus zr, this is equal to 0. So now note that from this equation already we have written 1 by a square as minus zp divided by x into c square. So here in this equation also we can write 1 by a square as minus 1 by c squared into p square plus z into r. So now replacing this 1 by a squared with this term, we will be getting minus zp divided by x c square. This is equal to minus 1 by c squared into p square plus zr. Now we can cancel this c on both sides and negative sign on both sides. We will be getting z is equal to x into, that is zp is equal to x into p square plus z into r. This is the required PDE. So we'll be getting this term, and the required PDE is nothing but zp equal to x into p square plus zr. Thank you.